All right, we're going to review for the final here. So that's in Blackboard under Final Exam Review, and here it is, finalexamreview.doc. All right, it is 50 multiple choice questions like last time. Bring your own Scantron, and it'll take place on the time listed on the syllabus, and which is Monday at 1:30, right? And I said I'd explain. So the university just has slots for Monday, Wednesday, Friday classes and Tuesday, Thursday classes. So this one fits in the Monday, Wednesday, because we don't meet on Mondays, but it still fits in the Monday, Wednesday slot. So that's why we meet at that particular time. If you do have a Monday 1 o'clock class, then you have a conflict. Does anybody have a Monday 1 o'clock class? Yeah. There aren't too many of those classes where there's a conflict, but every once in a while there is. So since nobody has a conflict,
I have a job.
yes. Yeah. If you have a really special circumstance, come talk to me. If you can get out of your job, then that'd be great. But if not, then yeah, come talk to me. All right. And hopefully, I always tell the story. Hopefully, I make it. One time, I actually did not show up for one of my classes final. That was like 5 years ago. Yeah. Well, no, back when Skeeter was the chair. Skeeter across the road was the chair. They called me up and said, "Hey, your classes there. Where are you?" But I usually don't space out. But because it's a different time, everybody spaces out once, and they're like, luckily I never did that as a student, only when I was getting paid to do it. Anyway, they passed the test out, and I got there. So. All right, I'll be there. So this is the test, okay? I did say, go back and review the lecture notes. The test is not really cumulative in that we don't test the kind of raw knowledge from before, but it does, the concepts build on each other, okay? So there are a couple questions where it'd be helpful to understand, it's always helpful to understand map projections. And we talked about when you do overlay, you want things to be in the same map projection. You don't need to know all the details about what a map projection is like you did in the first portion of the course, but you need to know things like that. So we talked a little bit about adjacency and containment in the lectures, where we mentioned how one of the fundamental things with spatial operations is looking at are things next to each other. That's adjacency. How much proximity is a measurement of adjacency, and then containment is something within a particular object. Those form the basis of lots of our spatial operations. And one of the things that you do need to know for spatial operations are basic overlay operations. So in that, I will limit it to, you should know what because these are all ones we talked about, or we did in lab. Intersect, union, and then, I don't know if we talked about too much in the lecture, but we did talk about erase. You should know what each of those does. And then we talked about clip in the lecture. I don't know if we ever did clip in the lab, but I think we did. So you should know those four for sure. Okay? So in intersect and in union, you should know that the attributes from each of the input layers will be included in the output layer. Okay? So if you have a number of attributes in one data set and a number of attributes in another data set, and you do a union or an intersect, it doesn't matter which, you'll get all of those attributes except for the shape and the feature ID. So I'm not talking about those. The shape and the feature ID, there'll still only be one shape and one feature ID column because there's just one for each of those. But all the others. So if you overlaid census data where you had population in 1990 and population in 2012 with county data where you had, maybe you only had county data and you had the name of every county. Now all the polygons will have those two population columns and they will have the column that represents the county. Okay? Intersect, union, both do that. The difference will be what? Anybody know what the difference will be between those two? In what? It's going to be the difference. The difference is going to be in the spatial data, the spatial result. So with intersect, you only get those areas where the spatial component intersected with the spatial component in the other data set. Okay, so you get the intersecting polygon. The intersecting polygons, these are polygon data sets, which a lot of times we're talking about polygons. I should pull up the actual lecture, but I'll just, I'm sure there's a picture that shows that. So here is, when we're doing an intersect, it's off the side, so I'll drag it over. When we're doing an intersect, if we have this layer and this layer, the output layer looks like that. Okay? It's the intersection of the two. Well, union would be like this. It doesn't say it's a union, but the input would look like this for one layer. The input would look like the circle for the other layer. And the result would be all of the areas together. Okay? Now, in the union, which polygons will have values? In other words, there won't be any nulls for all of the attributes. Let's say the circle represented a county and the polygons here represented parcels, just for fun. So which one would have all the parcel data and all of the county data? Which polygons would? They're not labeled, but yeah, the ones with both overlap. Now, the attribute table will have all of the columns in it, but it will have blanks in the county data for these for these two polygons, and it'll have blanks in the parcel data for this polygon. So that's the difference between a union and an intersect, is that a union will have all the data, intersect will have. We did a lot more intersects in this class than we did unions, but what's that? Okay, so that's overlay operations in vector. I'm looking at the test real quick here, making sure. Okay, when you do a intersect operation, when you do an intersect operation or a union operation, and there are different spatial dimensions. What's spatial dimension? What does that mean? What's the spatial dimension of a polygon data set? 2, right? Somebody said 2? Yes, that's correct. Spatial dimension of a line data set is 1. Spatial dimension of a point data set is 0. When you do overlay, the spatial dimension, you should know this, the spatial dimension will always be the smallest of the spatial dimensions used. So if you overlay points with polygons, you get points. Okay? I think I actually said almost all of this, but for intersect and union, it's true. And those are the ones that we're being tested on. So intersect and union, spatial dimension will always be the smallest of the two. I did notice a question, skipping back to adjacency and containment. We talked about different ways to express adjacency. And so there's a question that talks about it talks about how adjacency is dependent on the specific algorithm. Like, are you going to say that they share a common boundary or a common point? Typically, the main difference between adjacencies. That was on the slides. Okay. Another spatial operation that I haven't talked about yet, that's not an overlay operation, but it's a proximity operation, is buffering. What does buffering do? So if I had a question like, hey, I want to find all the areas within 30 meters of the roads, which of these operations is the appropriate operation? Buffer is the right answer. Okay. So that's that. I think that I've covered all the. There's no questions on slivers or how to remove those. That's a good question. So, but yeah, it's on the test. So like snapping, setting an error tolerance as part of a dissolve operation. Those are both ways to remove slivers, but neither one of those appear on the test right now. All right. Okay, raster analysis. So raster overlay is a little more of a different animal than vector overlay. Typically, it involves basic math. So you're adding two layers together to get a new layer. So we talked about how we could overlay two different layers that each represented the numbers represented polygon features, but they represented different land covers. How would you do that? Well, one way we talked about was you could multiply one of the layers by 10 and add them together, and each digit would represent one of those layers. So we talked about that. Let's see. We talked about different types of raster operations: local, neighborhood, zonal, and global. And you should be able to know what each of those are. Local operations basically look at one cell at a time and do an operation on that cell. Now, we can look at they look at one spatial location at a time. And so we can do that to multiple layers. In other words, we can add one layer to another layer. That's still a local operation, one spatial location at a time. That's different than a neighborhood or a focal operation that's looking at a moving window at the same time. It's considering a number of cells. So slope is one of the ones that does that, the slope operation. Also, just edge detection and I forgot what the other examples. I know we talked a little bit about edge detection. Oh, the neighborhood mean to smooth a layer would be a focal operation. A zonal operation is just finding out the statistic for a particular region of a raster data set. So a zonal operation would say, what's the average elevation within this polygon? And then finally, a global operation is kind of like a zonal operation, but for the entire data set. So what's the average of all of the cells? It's a special case. All right, that's the operation scope. All right, you don't have to make sure. All right, so you should be able to know what the kernel is for both a averaging 3x3 and an edge detection one, where you have on one side you have negative ones and on the other side you have positive ones. That would be trying to detect edges that run in a certain direction. Okay, so if they were on the top and the bottom, they'd be detecting edges north to south, on the left and right, east and west. You should know, well, that's under terrain. Well, let's see if there's any other questions. Right. Yep, exactly. That's exactly right. So the kernel is what you're multiplying each cell in that moving window by. The focus is usually the center cell, what you're assigning to the output raster. So one of the things that's important to remember, lots of students get confused, is that when it does the focus, it doesn't matter which way. We think of it going row by row. It doesn't really matter which way it's going because it's independent. It's calculating the kernel on the existing grid and storing the output in the output grid and then moving on. The existing grid doesn't change. So it's not considering that value in the output grid when it moves on. So it's calculating the neighborhood average, which means at every location in the output grid, you're just getting the average of the surrounding cells in the input grid. Smoothing that out or finding the edges. All right, so slope is actually a special case of a neighborhood operation, so is aspect. We did talk about how to calculate slope, and there are two different types of slope calculations that we talked about, whether you're using just the nearest 4 cells or the nearest 8 cells, but you don't actually have to calculate slope or aspect for what they are, but you should know what they are. So the slope is the change that's occurring, okay, and aspect is the direction of that change. What's a hillshade? And also, I didn't put it on here, but you should know that you can create a hillshade for analytical purposes or cartographic purposes. So for analytic purposes, you're trying to model the true location of the sun when you create the hillshade. For cartographic purposes, you're trying to make a map that looks good. And usually, you're actually going to put the sun in the upper left of the map, which it never really is in the Northern Hemisphere, but it makes it look proper. Which one? No, I did put hillshade, yeah. Okay, DEM, what it is, what it stands for, and what it is. So DEM stands for Digital Elevation Model. That is from the first part of the class, but you should still know that. And it is a raster data set where every cell represents the elevation at that location. That's what DEM is. Just as a review. But it is that same information. Since it's so vital in knowing terrain data sets, that's important. All right, you should go back and review the steps to water flow modeling. All the steps, where they are, which order you do them in. So you take your DEM, and the first step is, it's optional, but if you're going to do it, the first thing you do is fill the sinks, okay? And then the next step, after you fill the sinks, which basically just means that you're filling up all the pits where water wouldn't flow out of. The next step is to calculate flow direction. And flow direction just means for every cell, which way is water going to leave that cell. Okay, using the DEM, usually the filled DEM. The next step is flow accumulation. For every cell, how many cells flow into it? And I don't have it on here, okay, but you would want to proceed all the way through creating a watershed. So once you have flow accumulation, you could either zoom in and pick a pour point that was on the right place, or you just use snap pour point, and then finally watershed. So you know that whole flow to get to watershed. Okay. And what each one means. Okay, we talked about flow direction, but flow accumulation means for every cell, that's how many cells flow into that cell. For full accumulation, every cell's value is how many other cells in the DEM flow into that cell in the model. All right, we kind of spent a couple weeks on cartographic modeling, not really because I didn't give 2 lectures, but there were 2 labs, basically. So cartographic modeling, you should be able, there's actually not, like in the past I've had people draw a diagram out, but since it's going to be multiple choice, you should be able to recognize elements from a simple process diagram. So like, you know, if I make a simple process diagram and point out part of the process diagram, let's say what's going on here, or why am I doing that particular thing in that case. And they won't be they'll be all the tools that we've used in this class that we've just reviewed. So it'll be one of the overlay types we've done, or it will be one of the raster operations we just talked about. All right, what is cartographic modeling? That is the basically the process of let's see what the question says. All right, so the process of combining data sets, functions, GIS data sets, functions, and operations into a sequence to answer questions, typically producing an output map from various input maps is what? It's cartographic modeling. Okay. All right. Typically producing an output map from various input maps. So that's it. All right. Okay. Suitability modeling is a type of GIS modeling that attempts to find out which areas or which areas are suitable or how suitable those areas are for a particular activity. Suitability modeling is actually a pretty common task for GIS people. So it could be finding a new store, it could be putting in a new park, it could be, so there's, the point I'm trying to make is that there could be scientific or socioeconomic activities that are all really suitability modeling.
That's lab 11, right?
Yeah, lab 11. Yep. And that 10, really. So oftentimes cartographic modeling gets implemented for suitability modeling. Okay, standards and accuracy. We talked about 4 main types of standards discussed in class today. Let's see what the question says. Yeah, media standards, format standards, data accuracy standards, documentation standards are what we're looking for there. Okay, then you should also know the difference between accuracy and precision. Like, you know, looking back at what we talked about, you should be able to calculate percent accuracy from a table, okay, from a contingency table. You should know about RMSE. And, yeah. All right. Don't, I think that's pretty good summary of what what's on the test. Yeah. Oh, this isn't on the review sheet. The definition of topology. What's the definition of topology? I remember. It's the property of things being connected. So it's related to adjacency and connectivity. All right. Well, good. Anybody have any other questions? I already said not slope. You know, as I said, I need to make up 10 more questions. RMSE, maybe not. Maybe I won't make you calculate the actual value, but you should know, like, if I give you a list of a few and the error table, which one would be the most reasonable value. Remember, it's root mean squared error. But no. There are a couple of questions though that like give you a small raster and say, for this cell, which way would water flow out of it? There's some examples. If you go back to that lecture, there's a worksheet on that. So it's going to fall out to the greatest difference. So whichever cell has the biggest drop, it's going to fall in that direction. It's only going to go to one. Remember we talked about that's one of the weaknesses in that model, but that's the model that's implemented in most GIS. So it's only going to leave to the greatest drop. So the flow direction is always going to be the direction with the greatest drop in it. Any other questions? So there's nothing that's nested. Talking about nested functions on the test, but a conditional function is really a specific type of local operation, and yeah, you should know. You should know about that. So a conditional function says, okay, if this particular raster, I'm going to check every value. If it meets this condition, I'm going to reassign the value as either 1 or 0. It's a simple way to do a reclass conditional operation. And you should know the term, you should know the yeah, I mean, basically conditional operations, I should do it for you. It would be helpful to know, like, about like kind of just the logical operations. If I take a raster that's filled with values and I multiply by 1s and 0s, what's the output raster going to look like? So you can do those calculations because we're just talking about multiplication. So there is a question where you're going to have to do an operation like that on the test, but it's just addition and multiplication. So being able to go row by row, saying, okay, these are the two input grids. What's the output grid going to look like? If I'm going to add all the values or multiply the values. I mean, it's pretty easy and straightforward. If you can do addition and multiplication. Okay. But they'll all be really easy numbers, like less than 10 numbers. Okay, any other questions? All right. Cool. Cool. So I understand. I actually had 3 or 4 students ask if I was going to have time to answer questions today. So those must be more individual type questions.